My name is Andreas Farahmand, and I'd like to welcome you to another talk from the Machine Learning Advanced and Applications seminar series, which is co-organized by the Fields Institute and the Vector Institute. So today we have the pleasure of having Andreas Krause, who has done a lot of great research in machine learning. Many of you already know him, so it's not really needed to give a long introduction. So actually, I should say that I believe one of the first time I encountered Andreas' work was a paper on Gaussian process upper confidence bound, which was a very nice paper, and it turns out to be very influential. So I believe it got the ICML Test of Time Award in 2020. So let me briefly introduce him. Andreas is the professor of computer science at ETH Zurich. He served as academic co-director of the Swiss Data Science Center and chair of the ETH AI Center. Before that, he was an assistant professor of computer science at Caltech, and he received his PhD from CMU in 2008. He's a fellow of several institutes and received many prizes and awards. So just some examples that he's a Max Planck fellow at the Max Planck Institute, Ellis Fellow, Microsoft Research Faculty Fellow, and received prizes such as Russell Prize, which is from ETH, and grants from European Research Councils, NSF Carrier, and many others. So his research is also very recognized and received many awards from the community, including the ICML Test of Time Award in 2020 that I mentioned, and ACM SIG-KDD Test of Time Award in 2019. So Andreas served as the program co-chair for ICML 2018, and is regularly serving as area chairs or senior program committee members for basically all major machine learning venues. And today he's going to talk about safe and efficient exploration and reinforcement learning, which is a topic that I know many of us are interested in. So without any further ado, please join me in welcoming Andreas.
So can you see my slides?
Yeah? Yes, we can.
Yes. Okay, perfect. Okay, so thank you so much, Amir Masood, for this kind introduction. Thank you so much for inviting me. It's a great pleasure to be here, if only virtually. And today I'd like to tell you about some work that we have been doing on exploration and reinforcement learning, in particular thinking about safety and efficiency in this context. And this, of course, is joint work with a fantastic set of PhD students, postdocs, and senior collaborators that I'll acknowledge as we go along. So given this audience, I probably don't have to say too much about RL. Of course, it's this abstract model of an agent that's situated in an environment which it can affect by carrying out some actions, which might cause the environment to change its state and the agent to derive some reward from it. And the trouble is that our poor agent doesn't know how the world works. So it faces the dilemma of trading exploration, experimenting with actions to learn about their consequences, and exploitation, using what it learned in order to do well. And of course, this paradigm goes back several decades, both in machine learning and also in the area of control theory, in particular in the context of adaptive control. But we've, of course, also seen the pretty amazing advances in recent years, in particular in the area of games. And you can't really give a talk about RL these days without touting the amazing success and the landmark victory of AlphaZero's breakthrough in the game of Go. Now, I would say that a lot of the advances that we've seen are really restricted to settings where we have perfect or at least very accurate environmental models. And of course, the best example of this are games. So we know precisely how the Go board looks once we and our opponent have taken a move. And this means that exploration is primarily a computational concern. And it's pretty amazing how far clever algorithmic ideas like self-play and massive compute, the representational power of deep neural networks, can take us in solving such complex exploration tasks in complex games such as Go. On the other hand, if you think about applying RL in complex and often high stakes applications like optimizing energy efficiency of renewable energy systems, robotics applications, scientific applications in drug design, medical recommendations for treatments, etc., we rarely have an accurate model of the world, most an approximate one. And it means we need to learn one from data. And of course, data is expensive, but also exploration now not only becomes a concern of data efficiency, but potentially a dangerous proposition, right? It means effectively if we have to try actions with unknown consequences. And so we've gotten very interested in sort of trying to understand these aspects, both efficiency and safety of exploration in reinforcement learning. And in this talk, I'd like to give you a bit of an overview of several works that we've been doing in this space. And so I'll start to tell you about some work that we've been doing on safe Bayesian optimization. And let me start with a particular motivating example here. So we are collaborating with the Paul Scherrer Institute, that's the Federal Research Center in Switzerland, in using Bayesian optimization to optimize the performance of their free electron laser. So this is a 700-meter-long linear accelerator that generates X-ray pulses of extremely short duration, so femtosecond duration, 1/millionth of a billionth of a second. And so with this instrument, you can image extremely fast processes like molecules turning to each other in the context of a chemical reaction, for example. And this has, of course, huge applications from drug design to material discovery and so on. It's, of course, also a very complex machine with many literally moving parts. So the beam properties are shaped through a sequence of carefully arranged magnets that can be reconfigured and partly even moved around to optimize the beam properties. Now, also the properties of the beam depend very subtly on environmental conditions like temperature, humidity, etc., and also need to be constantly adapted to application domain requirements. So it's not just a setting that you have to find once, but it's actually a task where you constantly need to adjust this machine to match operating conditions. Now, in principle, one can sort of try to simulate the physics of this machine, but these simulations are extremely computationally expensive, and of course, also very difficult to really carefully reflect the effect of these environmental conditions that affect the beam properties. That means you effectively have to experiment while tuning this machine online, right? And safety indeed is a concern. So if you're not careful, what can happen is that there can be beam losses which may damage the magnets and require their replacements. And this you really don't want to happen. Otherwise, your collaborators will not let you use the machine again. Okay, and so fortunately, there are beam loss monitors installed in various places in this machine, which monitor essentially the critical performance. So they provide us some feedback signal. So on sort of a high level, we can sort of think about the problem essentially trying to optimize the performance of this black box, right, or free electron laser by sequentially injecting some controller parameters, theta t, that configure the magnets. We get some noisy reward signal, say the beam intensity, for example, that is perturbed by some noise. Moreover, we also get a measurement of how close we are to violating some of the safety constraints along it. Now, the trouble is that neither the objective F nor the constraint G are known ahead of time. So they're unknown. And so that means we need to close the loop to take the data we've collected so far in order to adjust these two parameters. So effectively, we have to optimize this unknown function F subject to unknown constraints G. And in order to ensure safety, we have to maintain feasibility of all iterates along the way. Now, it should be pretty obvious that in general, this is a completely hopeless task. So unless we make some sort of prior assumptions, we won't be able to get somewhere. And now one very natural way to encode prior assumptions is to take a Bayesian perspective. And that's exactly the perspective taken in Bayesian optimization, where we would endow our objective, maybe also our constraints, with some probabilistic model, which allows us to quantify uncertainty in our prediction. And that uncertainty can then be used in order to guide the exploration exploitation trade-off, as well as reason about safety in the process. Right, so effectively, we would treat the unknown objective or unknown constraint as one out of infinitely many possible realizations of the stochastic process, which we can condition on data under which the posterior distribution will contract. And of course, in principle, we're pretty free in what kind of Bayesian prior we might want to choose. A very common choice in Bayesian optimization are Gaussian process models. And a lot of, at least the theoretical work that I'm going to talk about, will rely on Gaussian process models whose smoothness and regularity properties are fully controlled by its covariance function that models how the function responds at two input parameters covariance. Later on, I'll tell you about how these results generalize to other types of Bayesian models like Bayesian neural networks. Now, here's sort of a key picture to understand how the predictive uncertainty can help navigate this exploration-exploitation dilemma. So suppose we've already carried out a bunch of experiments shown by these pluses here, and we can use this to condition and get a posterior distribution whose mode or mean is shown by this black line here. But moreover, we can also get, suppose we can get predictive confidence bounds shown in gray here, which are well calibrated in the sense that the true unknown function shown in this blue dashed line here is covered by them. If we can get ourselves in that position, we can apply the following reasoning. So we can look at the pessimistic estimate of the optimum, which is shown by this green dashed line here. So the best lower confidence bound. That means that with high probability, the optimum of our function should be somewhere above this green dashed line. That means we need to, we can focus our exploration to this green subset of the domain of plausible maximizers, where the upper confidence bound exceeds the best lower bound. And this kind of idea is at the heart of the optimism in the face of uncertainty principle, a central tenet in multi-arm bandits, reinforcement learning, and so on, in the context of Bayesian optimization and GPs that basically suggests being optimistic and that yields the GPUCB algorithm that was already briefly mentioned in the introduction. Now, of course, if we not only care about the reward, but also care about constraints, then maybe being too optimistic is also not the right thing to do. But fortunately, we can apply a similar reasoning, of course, to think about constraints. So if these are our confidence bounds now on the constraint function G, and we want to ensure that wherever we evaluate we are basically feasible, then we can simply compare a pessimistic estimate of our constraints, so the lower confidence bound, with the safety threshold, and restrict our exploration to this red subset of the domain where we can statistically certify safety. Now, these pictures are pretty intuitive, but of course, in order to apply them, we need to understand when can we actually construct these confidence estimates. And that itself is a really important question, one that we also have been looking at over the years, but there's lots of interesting open challenges here. So now, of course, starting with it, so if you sort of had a Bayesian model that really accurately describes the world, and we're interested in credible intervals at some point X, we might just take our mean and add some multiple times our standard deviation in order to enumerate the percentiles. But of course, we might not necessarily have a well-calibrated model, and the true objective or reward might lie out of the credible, outside the credible intervals of the Bayesian model. Now, fortunately, it's possible to actually recalibrate these confidence estimates so that they yield valid frequencies coverage with high probability, even under such circumstances, also for more general noise models, like general sub-Gaussian noise or even beyond, as long as we scale these confidence estimates in a way that depend on the complexity of the unknown function, here expressed in terms of the reproducing kernel Hilbert space norm associated with the covariance function that we use in our Gaussian process model, as well as an effective degrees of freedom, which basically quantify how quickly we can learn about this unknown objective. So this allows us and gives us some theoretical tools to understand under what sort of prior assumptions and regularity conditions we can get these well-calibrated confidence bounds that even hold for adaptively collected data, which of course is important for sequential decision tasks like Bayesian optimization or reinforcement learning. At this point, I just want to briefly point out, I mentioned many open questions. So one interesting one is to what these ideas can be extended to neural nets. And we have an upcoming AI stats paper that we look at sort of confidence estimates for neural networks through the lens of the neural tangent kernel as an analysis, just as a little bit of an outlook. Okay, now that we have some understanding when we might hope to get these calibrated confidence estimates, we can try to use them algorithmically. And the first algorithm that we proposed that does so, we call Safe Opt, and it basically works as follows. So we build our probabilistic models of the objective and the constraint, and we are going to constrain our exploration always within this statistical inner approximation of the feasible region. Now, one natural thing to do might be to just take a standard acquisition function like GPUCB, like optimistic exploration, and just restrict it to this red set in order to ensure safety. The problem with this is that it can quickly happen that the plausibly optimal actions here shown in green are contained in the strict interior of this red set, and hence there's no incentive to explore the boundary. We quickly get stuck in poor local optima. So one way to fix this is to explicitly reason about expansion. So we can also look at the subset of the domain here indicated by these purple points, where according to our confidence estimates, it's plausible that the outcome of an experiment would allow us to certify additional actions as safe and hence expand the set of actions which we can certify to be safe. Among those relevant points that could be plausibly optimal or expansive, we pick the most informative one and eventually find a better solution that's part of the domain. Now, under the same sort of regularity assumptions that we need for these confidence bounds to be valid, we can basically guarantee both safety and completeness about the resulting algorithm. So we can guarantee safety with high probability, and under different conditions, we can guarantee certain optimality properties of the algorithm as well. So for low-dimensional domains, we can guarantee convergence to a natural notion of reachable optimum. In higher dimensional domains, there's local notions of optima that I'm not going to elaborate more in this presentation here. And now, together with a bunch of additional tricks and to how to sort of scale this to reasonably high dimensional domains, like a few tens of dimensions, we can actually apply that algorithm on the free electron laser. So I'd like to show you some experiments that my students, Johannes and Monje, did running a variant of Safe Opt live on the machine. So we would look at the setting where we take configurations proposed by our physicist collaborators. We would detune the performance so that the beam has much lower intensity. And then we would use different algorithms in order to try to recover and find better solutions. And so what we can find here is that using the safe optimization, we can indeed recover or oftentimes find better solutions than the experts had initially provided, and also quite substantially outperform existing local search techniques that are widely used in this domain. Now, one challenge with Safe Opt is the following. From the description that I gave before, it should be pretty clear that we can really only hope to find the optimal solution or local optimum within the connected component of the feasible region that contains our initial starting point of exploration. By the way, this is something I should have pointed out. Next to the regularity assumptions, of course, you need to assume sort of an initial safe point, initial feasible point. Otherwise, the first action could be unsafe. Okay, and now here essentially we can hope to find sort of a good solution within this connected component, but of course there might be a disconnected part of the feasible region over here with a better solution that we'll never be able to find. Now this is a problem that existed for a while and that we now actually found a nice solution together with Sebastian Trimp's group and other collaborators at WTH Aachen, specifically for sort of safe tuning of dynamical systems, where we have the additional opportunity to observe a sequence of states that they undergo, and moreover, where the constraints effectively quantify distance to an unsafe set of states. So sort of an example, simple task to think about is this robot arm that's supposed to follow this target trajectory here, while maintaining some minimum safe distance to this wall here, right? Not bump against it. So here now we'll let the objective and the constraint both depend on our policy parameters or tuning parameters theta together with the initial state in which we would execute the trajectory. Now the key insight is that under Markovian dynamics, if we carry out a particular policy from some initial state S0 and observe the trajectory as shown by this purple trajectory here, then we can infer that the same set of parameters theta 0 is in fact safe for all states visited along that executed trajectory. And under similar regularity assumptions to those discussed before, this also allows to make some inferences on states that are sort of close by, right, in a way that's formalized in the paper. And so now this allows sort of a natural extension of the algorithm, where in principle, we can experiment with policy parameters, theta, that we can't certify to be safe. That might be plausibly safe, but we can't certify to be safe. So what you would do is you would simply carry out the trajectory and then observe once a certain boundary condition is met. And this boundary condition basically checks whether we can still guarantee that we will be able to, using one of the designated safe backup parameter settings that we already have established safety for before, you'll be able to safely recover. So once we check this boundary condition, we can basically always fall back to essentially these safe settings and recover. This now allows us to experiment with policy parameters for which we can't a priori actually guarantee safety, but because we are able to switch the policy online, we can safely recover. And this indeed allows us to find solutions that are strictly better than those found by Safe Opt. So here's an illustration on actual robot hardware. I'll show you a video in just a second, where at some point there's a jump because now the algorithm actually found a set of policy parameters that yield strictly better performance as before. So here's a little performance comparison. So there's the initial policy. So this robot arm here is supposed to follow this desired path, this reference trajectory. The initial policy is barely safe, and it's not very accurate in tracking this reference trajectory. So we optimize over these tuning parameters using Go Safe Opt and find a policy that tracks the reference trajectory much more accurately and is also more safe along. Okay, so this is some work on safe Bayesian optimization. There's been a bunch of really other exciting work by others in the community thinking about related ideas. There's one really nice paper I'd like to point out by Joel Burdick's group at Caltech, in particular with Yan and Sui, who was one of the co-authors of the Safe Opt paper, where they use safe Bayesian optimization to optimize therapies for spinal cord injured patients. That's a really exciting paper that I encourage you to take a look at. So one thing that this work on Go Safe Opt shows is that by looking more directly at sort of dynamical systems and observing state sequences and using the opportunity of applying these backup policies already suggests that we maybe should more directly look at dynamical systems. In particular, also the work that I've discussed so far really centers around Bayesian optimization, which is a viable technique in rather low dimensions, maybe a few tenths of dimensions. So what I want to explore now is a set of techniques that similarly makes use of these probabilistic confidence bounds to reason about safety and efficiency of exploration, but under much more complex dynamics, for example, as expressed as neural network policies. Okay, so we now want to learn to control unknown nonlinear dynamical systems. So here we focus on the discrete time setting, where we care about some unknown nonlinear function f. So focus primarily on deterministic dynamics, but these ideas generalized to stochastic ones with sub-Gaussian noise, where essentially this function maps our state action pair to the next state. One very nice opportunity that this more model-based setting offers is that it's very natural to incorporate, say, certain a priori assumptions about the model. So for example, from first principles knowledge, you might have an a priori model, and then you only need to learn non-parametric deviations. So you don't have to learn physics from scratch, right? So this is an idea that's, of course, been widely explored in robotics. It's very natural to think about, let's say, sim to real transfer, where maybe the simulation gives kind of the first principles a priori model, and we only need to learn where the simulator is wrong, or when sort of controlling complex dynamics like quadcopters, where first principles physics model might just well describe how the robot behaves in the air, but fails to account for complex turbulent ground effects, for example, right? And so this kind of perspective allows to only learn what's really needed in order to perform better. So I'd like to illustrate these ideas again on kind of a very simple RL Hello World example, the carpole, which is supposed to reach some target location, preferably without the pole falling to the ground. So instead of using these probabilistic confidence bounds to reason about rewards and costs, we're now going to use them in order to reason about the unknown dynamics. So that idea is pretty natural. So if you have our state space and some explicit subset of states that we don't want to reach, say the pole have fallen to the ground, what we could do is, of course, we can use these dynamics models to forecast plausible trajectories, right? So a certain prediction horizon, try to anticipate all plausible consequences for our actions. And now, then using ideas from robust optimization, we can try to ensure that under all plausible dynamics, we avoid unsafe states. And the main appeal now is that as we move around the state space, collect more and more data, explore, these confidence bounds contract, enabling higher performing and less conservative behaviors going forward. That's sort of the main idea. But of course, in order to make it work, there's a bunch of really difficult challenges. So one of them is that we really need multiple step ahead predictions. So if you use, for example, Gaussian process models, you would get nice elliptical sort of one step ahead predictions. But if you iterate them through the nonlinear dynamics, they get distorted in a quite complicated manner, which makes them quite unwieldy. And so one thing that we've explored in a recent CDC paper is how to conservatively over-approximate these resulting dynamics in a way that is sort of as tight as possible while still actually being safe. Now, unfortunately, even that is not enough because in order to ensure safety, it's often not enough to only look at ahead for a finite number of time steps, but you want to reason about long time horizons. So here's again sort of a simple toy example to think about this. So suppose we plan ahead 2 time steps with our carpool, right? So if these are sort of the next 2 steps we would reach if we were to go right around with our model, then we would conclude that we can safely move 1 step to the right. And again, right, expanding our prediction horizon by 2 steps, we would basically anticipate that we can safely continue. But now, of course, at this point, we've reached the point of no return. Right, we took that transition because 2 steps are safe, but now there's no way to return, and we're bound to eventually reach this unsafe state at the end. Okay, so now the key question is, can we still make use of these probabilistic confidence bounds in order to guarantee long-term infinite horizon safe behavior? And that's a question that we explored quite a bit in the group from various different perspectives, such as stability verification. So here's one way of how one can make use of these ideas in a model predictive control context. So let's look at our state space again with this undesirable states that we want to avoid. And let's suppose there's an additional subset of states here where we know we can stay. So for example, suppose we know we have a policy which has the property that the set as safe here is forward invariant. So essentially this policy is going to keep us within the set. So in this card pole example, we might know, for example, how to stabilize the pole when the card stands still. We don't know how to stabilize it if we go forward, right? But at least if we stand still, that's sort of is some prior knowledge that we can rely on. And now, of course, the question is how to make use of kind of this safe seed for further exploration. And one very natural way to do so is to essentially do the following. So we can first sort of try to plan a performance trajectory that, as usual, is maybe optimistic or trades exploration and exploitation. But at the same time, we come up with a fallback plan, sort of a plan B, that has the property that under all plausible trajectories, we guarantee to be able to return to the safe set. Now, what we're going to do is we're going to plan these 2 plans, plan A and B, at the same time and tie them together at the first action. And now the key benefit of this is that now, no matter what's the outcome of the first transition, in the worst case, we can always come back to the safe set. But if things go well, we can sort of continue going, collecting additional data and doing better. Okay, so that's basically the idea. And again, under the same sort of regularity conditions that yield valid 1-step confidence intervals, essentially one can guarantee formally long-term safety properties of that resulting algorithm. So here's a little illustration on this card pole example. Now we basically use Gaussian process dynamics models to forecast plausible consequences of our actions. And we use neural network policies to optimize the resulting controller. So we compare, against a baseline method, which essentially plans ahead only for a finite prediction horizon, so it doesn't ensure this long-term safety property, but otherwise still use the same kind of dynamics model to implement chance constraints to avoid constraint violation. Now, this algorithm is very effective, very quickly finds a near optimal policy for this task, but since it only plans ahead for a finite number of times, it can sometimes not avoid these failures that really require looking ahead longer. In contrast, The algorithm that I've described to you before takes longer to essentially find the optimal policy. On the other hand, it's able to completely avoid failures along the way. Now, this is arguably still a very simple example, kind of a hello world RL task. So one thing that we've been very actively working on recently is trying to push these ideas and scale them up to more complex deep reinforcement learning settings. And that's what I'd like to talk about next in this talk. And so in particular, for now, let me disregard safety. We'll come back to safety later and purely think about efficiency of exploration. And so one common paradigm that's often considered for sort of improving sample efficiency in reinforcement learning is the model-based setting, where essentially we sort of consider a setting where the agent goes through a sequence of episodes. Each episode, we maintain a behavioral policy that we would roll out by really interacting with the environment, exploring life, collecting data. And now we would use that data along with past or offline data that's available to us, refine our estimate of the transition model. And then introspectively, we would use that model in order to plan offline a policy, a new behavioral policy to be rolled out in the next iteration. That's kind of a standard template for model-based reinforcement learning. So generally, of course, the goal is to optimize over our policies pi for the long-term discounted sum of rewards with respect to the underlying MVP. Now, of course, trouble is, and that's kind of the primary setting we are interested in here, is the setting where the underlying macro decision process is actually not known to us. So one, of course, natural way to sort of deal with this uncertainty is to apply the optimistic principle and essentially not just consider the unknown model, but consider all possible plausible dynamics models. And this idea is at the heart of algorithms like UCRL in the tabular setting to implement this optimism in the face of uncertainty principle. Now, the trouble is that in general, this is a very difficult optimization problem because we have this nested optimization. The outside, we optimize over policies. In the inside, we optimize over all different dynamics models that are consistent with the data. That's sort of a very difficult optimization problem to solve. That means that instead, oftentimes, what's done is to replace kind of the optimistic estimate purely by sort of a greedy exploitation. So you would basically keep track of the distribution of our plausible dynamics models and optimize the expected performance where the expectation is drawn from models drawn from that posterior distribution. And this idea is at the heart of the seminal Pilko algorithm proposed a number of years back that really showed how model-based RL can help dramatically in terms of sample efficiency. And it's modern instantiations like the PETS algorithm, for example, that uses probabilistic neural network ensembles. Okay, so and the benefit of sort of this greedy exploitation is one can use standard black box algorithms, often model-free algorithms, for solving the planning step in model-based RL. Now, what we recently figured out is how we can indeed actually solve optimistic exploration, so optimize over these confidence bounds, but using essentially black box tools from standard reinforcement learning, in particular model-free planning algorithms. And the key idea is the reduction. So the key idea is to turn this optimization over plausible dynamics into just yet another policy. So essentially allow the agent to optimize over its own luck, to control its luck, so to say. I'm going to explain that in just a second, but under GP dynamics models and the same sort of regularity assumptions, we can actually guarantee regret bounds for that algorithm. So I'm not going to talk about theory much here, but the algorithms now can actually use much more complex dynamics models like probabilistic ensembles, for example, as I'll demonstrate in a moment. So here's kind of a one-dimensional cartoon of the algorithm. So x-axis is time. Y-axis is a one-dimensional state space. We have an initial starting state as 0 and want to reach a state with a sparse reward signal. Now, what we would normally do is, of course, pick a policy, right, that predicts the most likely next state. But of course, there's some uncertainty attached due to the epistemic uncertainty of the agent of not knowing what the true dynamics model really is. So instead of considering all possible outcomes, what we're going to do is we're going to allow the agent to optimize, to pick where it wants to end up within these one-step confidence estimates. So essentially, we learn another policy, a state-dependent function that essentially tells us where within this confidence set we end up with. In concatenation with the policy pi just yields basically an optimistic next state, S1 tilde. And then, of course, we just iterate, again, following our policy pi, allowing the agent to hallucinate control over its epistemic uncertainty to pursue this optimistic trajectory, which yields the sparse returns. And that structurally now is the same form as sort of a standard approximate dynamic programming problem. And we can use standard model-free reinforcement learning algorithms in order to optimize the performance. So here's a little illustration on, again, sort of a simple inverted pendulum task. Of course, the task is to swing up that pendulum to the upright position. So I'm going to show you sort of the model's predictions and the real trajectories. So the x-axis essentially shows what the model thinks it can do when controlling its luck. And so it's very optimistic. It believes that it can immediately swing up the pendulum to the upright position. But then, of course, when it tries it out in practice, it's disappointed. On the other hand, it at least collects a little bit of data in the region around the starting state, which contracts the confidence bounds, restricts the control authority of controlling its own luck. And after 2 more episodes, the agent basically has figured out that it needs to swing in one direction until it can swing up on the other direction. That's what the optimistic trajectory says. In real life, unfortunately, still doesn't quite work, but of course, you explore a larger part of the state space. And keeping going, after 5 episodes, it's not actually able to swing up, but it slightly overshoots because it hasn't collected any data near the upright position, which is quickly fixed. And after about 7 episodes, it basically has found the optimal policy for this task. So that's the cartoon, but now you can do it on more complex settings, like the Mujoco suite of sort of simulated robots. Here's the Half-Cheetah, so one of these benchmark tasks. And so we compare against PETS, which is basically a standard model-based reinforcement learning algorithm that uses probabilistic dynamics models, but just uses greedy exploitation. And this already works quite well in this task and finds good policies quickly, far more quickly than model-free counterparts. Another common example for sort of exploration in Bayesian models is Thompson sampling or posterior sampling, where you would sample a dynamics model from your posterior and then simply optimize it. This helps a little bit, but you can still do quite substantially better than doing this optimistic plan. Now, this is just on sort of the standard problem instance, but it turns out the difference becomes more pronounced if you make exploration harder. One way to make exploration harder is to increase action penalties. So these are basically additional regularizers encouraging small forces to be applied to the robot's joints, which often makes sense in real-world applications. But it has the effect that it effectively pushes sort of policy search methods to do nothing, right? To essentially pick the 0 action and don't change the robot's position. And so as you increase the action penalty, this effect gets more and more pronounced. And eventually, greedy exploitation has a very hard time learning. So does Thompson sampling, but this optimistic exploration still has no trouble finding a good policy. And just to sort of get a bit of an intuition, so if you have small action penalties, it's perfectly fine to move the robot forward by doing things like this here, right? By vigorously waving with your extremities, you can still sort of happen to go forward, but that's no longer possible if you have to also suffer from these action penalties, and hence you need to be more careful in what you do. This avoids these aggressive controls. Okay, so it makes exploration much harder, but optimism still allows you to find good policies. Now, this shows how one can implement these ideas of sort of using confidence intervals for now the dynamics in order to improve efficiency of exploration. So natural question is sort of, what about safety, right? Given the title of the talk. And one natural way to sort of think about safety, maybe arguably the most common way these days to think about safety in RL, is through the constraint MDP paradigm. So instead of just optimizing the expected returns in terms of reward, we would also have a separate cost function where you essentially want to minimize a sum of costs with a separate cost function that maps states to costs. And so one common choice might, for example, for the cost function to just indicate the unsafe states, in which case the constraint effectively controls the failure probability or the probability of visiting unsafe states for the agent. And this, of course, is the ideal nominal approximate dynamic programming problem that you'd like to solve if you were to know the unknown MDP F star or constraint MDP F star. And of course, the trouble is, if you don't know it, what you do instead. And so based on the ideas developed in this talk, a very natural way to sort of instead is to basically be optimistic now with respect to the reward, while being pessimistic with respect to the costs. Okay, and so that naturally yields kind of an optimistic, pessimistic CMDP. And in an upcoming ICLEAR paper, we present a method for basically solving that resulting constraint MDP to find solutions in this model-based RL fashion, right? So use the solver to essentially plan offline a solution to this constraint MDP, deploy it, collect data, and proceed. Now we demonstrated on the OpenAI Safety Gym benchmark suite. There's a bunch of sort of simple robot models, like a simple point mass, simulated slightly more complex dynamics in a car model, and a simple quadruped robot. There's a bunch of different tasks, like reaching a goal, touching a button, pushing an object to a certain location, and so on. There's also various different sensing modalities that the robot has. So we really look at the challenge of essentially planning for pixels. So we look at proprioceptive feedback. So basically the robot has a front-facing camera, and that's what the agent gets to see. And of course, this leads to substantial partial observability issues, which we address using recurrent neural nets, in particular the recurrent state space model architecture proposed in the Halfner et al. Paper, which we extend to sort of a Bayesian setting. And in sort of the terminology analogy from the Halfner et al. Paper, the algorithm sort of dreams about consequences of its action, maybe sort of dreams about optimistic outcomes of what could possibly happen with their policy, while at the same time facing nightmares about what might happen in terms of constraint violation. And now this algorithm is actually indeed able to find feasible policies for all these benchmark tasks from proprioceptive feedback after about 1,000 episodes with about 1,000 environment interactions. And we compare against a bunch of baseline methods. So contemporary model-based method that uses a similar variant of model predictive chance constraint model predictive control, a bit similar to the ideas discussed in the carpool example earlier, as well as several model-free alternatives. So this plot here shows normalized metrics in terms of the reward, the safety during training, and the safety after training. So basically for deployment, we normalize such that the algorithms are scaled between 0 and 1, with higher being the better. And here, after the same number of interactions with the environment, so 1 million environment interactions, this new model-based algorithm actually substantially outperforms these baselines in all the different metrics. There's also a bunch of different ablations. For example, we compare against an unsafe version of the planning algorithm that doesn't care about the constraints to sort of look at the upper bound and the performance. And so oftentimes you can reach sort of similar performance on those tasks, while of course doing much better in terms of the resulting safety metrics. Also in comparison with the model-free RL alternatives, we allow them to have a lot more environment interactions, in this case 10 million environment interactions. And even after observing basically 10 times as many interactions, the algorithm still does competitively in terms of rewards compared to methods like CPO, while doing better in terms of constraint satisfaction. So how are we doing in time? I guess there's a few more minutes. There's one last topic I could briefly talk about, but I'm also happy to skip to the end if you like. So one central ingredient, of course, in all the algorithms that I've discussed are these probabilistic models, right? And they need to be well calibrated in order to give us good confidence estimates, both for sort of the rewards or costs in safe Bayesian optimization, or the dynamics model and model-based RL, and so on, right? That's sort of a central challenge. And of course, one way to go about them is to hand design them. Maybe to some extent, it's possible to do this, right? By hand designing kernel function for GPs. Maybe you can do this in situations where you know something about the Lipschitz constants. Maybe you have sort of a good prior for sort of from the first principles physics model. But of course, a very natural, appealing alternative would be to try to learn sort of these priors from data, or sort of from related tasks. And that's a direction that we've been very actively exploring and looking at recently, in particular through the lens of meta-learning, where we, in this case, actually want to meta-learn a probabilistic model, right? So starting from a bunch of sort of observed prior data sets, you would use sort of a general purpose meta-learning algorithm that, starting from a hyper prior, would generate a hyper posterior, which then serves as a prior for the downstream based learning task, right? Would, for example, meta-learn a covariance function of a Gaussian process model, or a sort of a weight distribution for Bayesian neural network learners. And of course, there's various different ways of how to do this. So we follow some really cool work by Pentina and Lampert and Amit and Meyer that pioneered perspectives of PAC-Bayesian meta-learning on, so essentially deriving cost functions for meta-learning in this, that are essentially derived from minimizing a PAC-Bayesian generalization bound on the transfer error across related tasks. And so in this ICML paper, you observe that if you plug in the optimal base learner, it actually turns out to be tightly connected to approximate Bayesian inference. And as such, one can characterize what's the so-called optimal hyperposterior. And it turns out the resulting cost function actually looks a lot like cost functions that arise when doing approximate Bayesian inference in Bayesian deep learning. So you can use a lot of the standard inference algorithms, variational inference, time variational gradient descent, and others in order to optimize this upper bound on the cost function. And that actually yields algorithms and models that perform really quite well on challenging tasks. So here's a little bit of a qualitative illustration. So here we train the algorithm just with very simple tasks, each of which correspond basically to a sine wave. So each colored cloud of points corresponds to sort of one regression task. These are all essentially generated from sine waves with slightly shifted phases and frequencies. The training examples per task are very sparse. So from each task, we only observe about 5 samples. Then we use the algorithm to essentially learn this hyperposterior, and on the right plot shows a bunch of draws from this hyperposterior, and they all sort of look like these sine curves. So they sort of capture this qualitative behavior, and not surprisingly, yield much more calibrated and more accurate predictions, in particular in the context of little data. So if you just use standard Bayesian neural net priors with isotropic weights, it's often very difficult to calibrate them in order to get meaningful uncertainty estimates, versus these essentially PAC-learned priors yield much better, much more calibrated confidence estimates. There's a bunch of experiments that we report in the ICML paper on both medical time series forecasting application, as well as on the SwissFel data set. So where essentially each task corresponds to a different tuning session of the laser. Here's some results in terms of predictive performance, comparing this PAC optimal hyperposterior, both with GP and neural network posteriors, with various forms of, for example, model agnostic meta-learning, previous work on PAC-Bayesian meta-learning, neural processes, and of course, non-meta-learned models, and yield, in some cases, quite substantial improvements in terms of predictive performance, here RMSE, but also uncertainty calibration, quantified, for example, by looking at accuracy of predicted versus estimated quantiles of the predictive distributions. So again, in these examples, the approach yields state-of-the-art calibration of the resulting probabilistic models. And those turn out to be really, really useful for sequential decision tasks. So here's some reports using this algorithm in a Bayesian optimization context on a task that is motivated by a drug design application. So essentially, our job is to pick a protein out of a collection of protein candidates for one that maximizes binding affinity with respect to a certain receptor molecule. That's kind of prototypical for many experimental design tasks that arise in drug design and related applications. And it's sort of a very natural closed loop setting where you essentially have this black box, right, the binding affinity, which you would like to optimize by choosing from a pool of different candidates in a closed loop fashion. But it's also a setting where there's oftentimes many related Bayesian optimization problems. So for example, you might want to optimize not just with respect to one, but multiple target receptor molecules. And so it's very natural to sort of take prior training data from past targets for which already you've optimized in order to try to accelerate optimization for sort of a new related problem. And sort of overall Bayesian optimization as its main appeal, the benefit of relying on prior knowledge in order to accelerate optimization, right? So if you just have an uninformed prior, one can't really expect Bayesian optimization to do a lot better than techniques like random search. But if one can have an informed prior, either through hand design or possibly meta-learning, there's the chance that you would actually get better performance. And that's what we really see in experiments, right? So this PAC-learned meta-learning model essentially yields to much better convergence, essentially finding much better solutions much more quickly, much more sample efficient manner. Okay, so that's basically brings me to the end of the talk. So I think if you really want to harness this potential of reinforcement learning in challenging real world applications and get closer to sort of this idealized model of an agent learning much like we do in the real world by interacting with the environment, we'll have to up our game in terms of efficiency and safety of exploration next to many other challenges, of course, that are faced there. So it's a really exciting research field, many open questions and lots of exciting things to do. So I'd like to conclude here by thanking all my collaborators on this research program, the students, postdocs, and senior collaborators, thanking all of you for listening. Here's a few references if you want to read up more on some of the work that I've discussed. There's also a tutorial that I gave at Koller a little while back on some of these ideas. And I'd be very happy to answer any questions you might have. Thank you very much.
Thank you very much. It was a very interesting talk. So I think we have a few minutes for questions. And also I just want to mention that we have a roundtable after 4 until 4:30. So if you want to chat more, feel free to stay around. So I think there is already a question by Florian. Please go ahead.
Hi, Andreas. Thanks for the excellent talk. So I was wondering if you could comment a bit on cases where the constrained MDP approach to safe exploration might fail when we translate it from theory into numerical optimization, particularly in cases where the unsafe set is very small. So bad situations are very rare but catastrophic. So in those cases, presumably your cost function would be, you wouldn't be able to estimate your cost function very reliably.
Yes.
So what types of ideas do you have for addressing those scenarios?
Yes, it's a great question, right? And I think the maybe more general question is kind of, if you really want to insist on safe exploration, what can you latch onto, right? So what kind of prior assumptions are reasonable, right? And that, I think, is a largely open question, right? So I think one natural starting point is certainly to maybe have kind of a safe initial policy, right? Maybe some safe set of states that you can retreat on, but even keeping track of this, verifying this in high dimensions is challenging and so on, right? So in general, sort of learning about a small set of really catastrophic states without any prior assumptions is bound to fail, right? So it's a bit unclear really what one can leverage, right? And I think there's many many really interesting open research challenges here, right? So somewhere prior knowledge needs to come in, right? Either being hand designed, maybe learned from related tasks, right? Maybe specified through formal languages. I don't know, right? So I think there's a large design space, but in general, it's wide open. But thanks for the question.
Thank you.
Any other questions?
Taylor has a question.
Yeah, Andreas, thank you so much for visiting us virtually and staying up late. I was curious, so I work primarily in offline settings in some of these safety critical domains that you talked about, where exploration is not feasible and optimality is infeasible as well because we have limited data. What kinds of insights could a researcher such as myself draw from some of these things that you've been exploring about safe or upper confidence bounds?
Sure. No, a great question. So, I mean, in general, I think that's sort of a nice perspective that in general, the model-based paradigm offers, right? Because I mean, the data I mean, generally, you can use arbitrary off-policy data, right? And so that could come from prior exploration, could be from pure exploration tasks, right? And I think similar questions on sort of reasoning about pessimistic consequences of your actions, I mean, to some extent, are already quite naturally explored in offline RL, in particular in more sort of the model-free setting, right? But also make a lot of sense in the model-based setting. So I think that it's very naturally connected. I don't think there's necessarily a discrepancy between sort of offline RL. And,
right. Like I think that part of where like I really appreciate the work that you've done and the notion of saying like what's the information we need in this exploration step based off of the UCB constraints that we've created, but a lot of the, I think, inductive bias that you're gaining through sort of these iterative processes of exploring and learning really benefits sort of that sort of estimation where we are not guaranteed that type of performance improvement in offline settings, and you're only as good as the data that you have or your understanding of the physical world that you're trying to model.
Yeah, I agree. Thanks.
So I'm kind of wondering if there's another question. So actually, maybe I have a question. So the method, I guess lambda method that you mentioned is kind of combination of optimism in face of uncertainty using a constraint MDP framework. So another way, I mean, to encourage or balancing exploration exploitation is through using something like Thompson sampling. What do you think of a combination of Thompson sampling but using essentially constraint MDP type of framework that we sample from a posterior, solve the constraint MDP, and then act based on that?
Yeah, it's an interesting question, right? So Thompson sampling is a very good idea for sort of exploration, and also oftentimes leads to very effective algorithms because you sort of just have to optimize your posterior sampling. For the constraint setting, it's a little unclear, right? So it behaves very much kind of like optimistic exploration, and of course has the similar challenges, right? That's being too optimistic is problematic if safety is a concern, right? So purely, say, Thompson sampling the objective and the constraints will not work, right? It's easy to construct counter examples, right? Because I mean, you might just have an optimistic sample of your constraints, right? And what can you conclude from it? So this certainly will not work. To what extent one can borrow ideas from Thompson sampling and then maybe associated tools to also ensure safety? Yeah, I think it's an interesting question. I don't have an answer to that.
Okay. Do we have any other question?
I have one more if we have time. So I was wondering if we let go of the notion that the agent has to be safe with some very large probability. What type of avenues are opening up in the sense that you might have agents that might have, sublinear regret. You might have agents that really learn fast from their mistakes. So how would our methodology become different if we let go of the notion that our agents have to be super safe all the time?
Yeah, I think it's an interesting question. It depends on sort of what is acceptable and what's not acceptable, right? So if maybe you have 10 robots that you get to destroy, right? How do you pick them in order so which policies to deploy in there, right? In order to learn as much as possible. Yeah, I mean, there's various different settings one can imagine, but sort of converging really on a formalism that makes sense is maybe take some iterations.
Got it. Thank you.
All right. If there is no other question, maybe we can shift to the next part, the roundtable. So feel free to stay and have a chat with Andreas. And let's thank again Andreas for the great talk.
Thanks a lot, everyone.